Okay, we are live.
Should we start letting people in now if y'all are ready?
Okay, should we get going? Okay, hello everyone. I'm Risa Madoff. Thank you for joining EPSP Connects for today's science talk. I'll be moderating questions with Jimmy Geilinger. And before I introduce our speaker, I just want to remind everyone that next month in April, we'll be hosting a panel discussion on building a supportive research community, and that'll be on April 21st. So please consult our website for details and registration. Okay, well, we are pleased to have Irina Overeem today, currently an associate professor at University of Colorado Boulder and in geological sciences. And her current research focuses on river and coastal system dynamics and their response to environmental change. In today's talk, she'll be looking at how climate warming is affecting sediment transport and geomorphology in cold, icy landscapes. Okay, just to remind you, we'll be taking questions at the end, and we'd prefer if you could input your questions into the chat, and so that we can monitor them, and I'll try to read them off, and if they're kind of long, I'll probably ask you to unmute, or we'll unmute you to ask them yourself. Okay, so with no further ado, I'll hand it over to Irina.
Thank you, Risa, for a great introduction, and thank you for the committee for inviting me to speak to the AGU EPSP community. I guess I'll make sure that everybody sees these slides all right. Is that true? Yes. Okay, thanks. So today I'll be talking about ongoing project work that is happening in our group here at CU. It consists some of modeling that we do quite a bit of in our lab. My team's closely associated with the community surface dynamics modeling system here at CU as well. And we had been working on a cyber infrastructure project that was focused on permafrost landscapes, but much on the modeling side of things. And only recently have started a new project in which we're also going to collect process data observations on the North Slope of Alaska. What I'll show today is more on the modeling side. And these are like key papers that have been worked on of like a pretty large collaborative team, but like key players are Kang Wang and Lei Zheng. And then it was collaboration with Gary Clow and Elchin Yafarov on the permafrost modeling. And then I also have somewhat fresher results of like data and model analysis combinations that Anastasia Biliouros and Jaap Nienhuis and I have been working over in the last year or so. So I said like a lot of what I'll show today is like modeling work. And I think that holds up in the sense that we're at a stage where we have like all these predictions about the landscape based on numerical modeling results. And I'll walk you through those. But I think where we are at is that those predictions are like hypothesis generating again. And like they would have implications, but I'm like keen to like go back to observations again and sort of like tie down, is this really what's happening? Is this really what is happening in the landscape? Can we constrain it better when we look at the actual processes in the field or at the field scale? So the premise or sort of background of where we're looking at these climate change processes and processes, how that affects sediment transport and sediment all the way from source to sink, is the fact that over the last decades, global warming has been much amplified in the coldest regions of Earth. Not just the Arctic, which is like maybe the more known quantity, but also the Tibetan Plateau actually. And I'll point to like a paper that I don't have enough time to like really highlight much of, but that we also worked on on the Tibetan Plateau and sediment fluxes there. But so this idea of the highest, coldest regions of Earth seeing a much more rapid warming trend sets a sort of a scene and an experiment for us to look at the landscape and like, how is that changing with rapid warming? And in the cryosphere and Arctic community, this has now been studied for like 25 years or so. And the study of Arctic change, which is a big overarching committee in the US, laid out like the connections between the system parts. So sea ice being studied, land ice being studied, permafrost being studied, and all those elements of the cryosphere and the big feedback loops. One in the sense of the sea ice albedo effect, so white sea ice reflecting heat into space and changes that happen there. And then the feedback loop of permafrost thawing and exposing new carbon. And so like that, those are these like, that's this little green box here. But most of what they talk about is either like cryospheric elements or they're like big climate processes, right? And then in our community, like the other paper that's sort of like the twin paper that goes with this one is by a large committee led by John Pelletier, where they were like laying out like what are our challenges as a community in the surface processes. We know all these forcing factors are changing. How does that affect secondary processes like runoff or waves? And then like how does that impact geomorphology? And so what I'll advocate a bit for today is, are some of these feedback loops also impacted by the geomorphic processes? And do we give them enough attention? Is that something that in the climate community is being missed? And do we as a Earth surface processes community not think enough about how these changes in the geomorphic processes feed back into the climate system. I mean, that sounds like a big task, and like, of course, I'm not going to fulfill that like really big task. But the part where I'll focus into is that feedback loop of the permafrost carbon feedback. And so the idea is, if you have large regions of permafrost in the northern hemisphere, and they have in their soils that are now completely frozen for like a large part of the year, and only thaw out to like a part of shallow active layer, shallow depth. What if you should thaw that out way deeper? Then you're starting to expose carbon that's been frozen and had been stocked in the soil from previous interglacials, and you potentially could expose that to microbial decay, for example. So like you expose it to the atmosphere potentially. And so what I am interested in is what if that starts moving around, and how will it start moving around? Will it get deposited like straight away and like be stored in riverbanks straight away or in river point bars? Are these changes in thaw also changing sediment transport processes? Right? And so this combination of sediment transport and the associated carbon cycle is what we're trying to like figure out. And then some of the work that we've been doing is like a bit more in the sort of trajectory out in the century to come. So where I'll start is on a small river basin scale. So maybe these rivers are about 125 kilometers long or so. They are located in the continuous permafrost zone. So this is Alaska, and these are part of the National Arctic Wildlife Refuge in northern Alaska. This is the Beaufort Sea, so they're really far northern rivers. Over the Brooks Range, north of the Brooks Range, like the Brooks Range splits the National Arctic Wildlife Refuge in sort of two areas that are climatologically a little bit different. So the highest peaks are about 2,500 meters, and then it goes all the way to the coastal zone that I was more familiar with from previous work, where there's a lot of coastal erosion happening. And so we delineated three sort of hydrological units. This was on a Corso DEM before the Arctic DEM, or so they're like combined river basins. They're not all like individual one rivers, but there are like a couple combined rivers often. So here's a bit of a map view of that. You can kind of see the Brooks Range being in the south and high, and then the Beaufort Sea in the north. Sea ice covered until July every single year, to set the scene. And then these rivers are frozen 7 to 9 months a year, and only thaw out late May and keep running maybe to late September. And these are not rivers that are gauged, so that's not a very good pick in that sense. But there's few of the rivers on the North Slope that are gauged. So we set up a sort of a combination between model and data. And the core is in these green boxes. Those are the two models that are combined. That is the Geophysical Institute permafrost model, and that is going to help me predict thermal state. So it's basically a temperature prediction model. It takes air temperature or ground temperature and propagates that into a soil column. It is a plan view of these, but in the end, it's individual columns that are like all like lined up together. There's many layers in the columns, and they go very deep because I'm running this for 100 years and I want it to be like thermally undisturbed on a 100-year sort of warming cycle. So the columns are about 100 meters thick. We drive the model with either data that's downscaled meteorological data from like observed and then gridded, Or if we look at the future, we pull from the climate models, we pull a subset of 5 best performing models in Alaska, and we drive like temperature and precipitation with that. Snow is a very critical part of a permafrost soil combination system and the thermal coupling between that. It acts as an insulator basically. So we didn't want to disregard that, and we have an empirical snow model in between that can act as that insulator. Here's where it gets a little bit more soil and geomorphically interesting. We pulled in from Soil Grid, which is actually a new CSDMS data component. So like I'll advertise for that. We pull in soil types at a 1 by 1 kilometer resolution and convert those to thermal properties, because that's what needed to actually predict the thermal state of soils in a watershed. The other thing we pull is the soil carbon database that the Permafrost Carbon Network has put together. And so much of what I said about this permafrost carbon feedback comes from that community putting together like a really large database and like an understanding of like, where is carbon in the landscape? How much is there? Like, where do we have measurements? Where don't we? They're typically to like about the first 3 meters is where they have data. And so what are the things that I predict? Well, temperature, and that's my thermal state. But then the other thing that's maybe the part where geomorphologists or process people get interested is active layer thickness. And so one way to look at that is it's just like how far the thaw front, how deep the thaw front penetrates into the soil that year. And then like everything below it is permanently frozen and is, whereas then that like freezes again in the winter, and then the next summer it comes down again, right? If that gets deeper and deeper, we have more and more mobile regolith or mobile soil potentially to like move around in the landscape. And then with that thawing, I also look at how much carbon do I newly expose. So here's a little like layout of what those parameters are and where they came from. Maybe the things to take away is we ran this at monthly resolution, which I think is a justified way of doing this. We're not looking at like really detailed event-based dynamics at this stage yet. We're trying to like sort of capture like what is going to happen in this landscape. Are we generating more mobile soil? Where are we generating it? Where are we generating carbon? We are acutely aware, this is Kang and I, we are acutely aware that these model inputs are generalized data sets. That's true for the reanalysis data set, that's true for the soil data sets, et cetera, et cetera. So that means that validation is important. It also means that we immediately can see shortcomings once we start comparing to like actual permafrost data stations, for example. So like here's a bit of an idea of like what can I see when I look at like model data in the orange over a few year cycles, like this is a decade or so. And then in blue are like the observations at a particular station. And so what we found is that the thermal state is actually relatively well predicted for few data points, right? There's not that many of these stations. Snow depth is reasonable, sometimes some years more often than other years. And active layer thickness captures the mean, but not so much the like yearly variation. So like if any year there's like some discrepancy between these data sets, or the snow depth was wrong, whatever, you get like the actual value for that year might be somewhat off. How about if we look a little bit deeper into the profile? That should be a more robust metric because we're like deeper into the permafrost, so it's more of a signal of like a few decades of warming. So we're lucky that in the National Wildlife Refuge, there's been borehole measurements, so deeper measurements, and they have been repeated over the years. And so this is a transect that goes from the coastland inward. And you can see that in blue is what our model predicts for that year. And in little brown dots is what was measured in these boreholes. They're old petroleum wells that are abandoned and that now get used for temperature measurements. And so here we are like actually pretty satisfied with what the model is doing over sort of a couple decades of scale. It captures that trend well, where the coast is way colder, the permafrost is way colder, and it warms a little bit inland, which is counterintuitive often to like people who are like thinking about, oh, I'm going higher up in the landscape and it gets colder. Here, that's not so much the case, which is the sea ice and the ocean cold dominance here makes the landscape cold there too. So when I run this model, so like remember we had these like 3 basins next to each other. So like we have like 2 or 3 rivers here, like 2 rivers here, and then like another one like here at the side. This is the Beaufort Sea, and then this is like the high point is the Brooks Range. And what I'm going to show you is the ground temperature at 2 meters, mean annual ground temperature, and it like will pulse every single year, right? It runs through like a cycle of warming through every summer. And then on the left-hand side, you're watching historical data. And on the other side, it is if we use a fairly extreme warming scenario, what happens then to soil temperatures. And so what you can see now that this is run is maybe the big thing to take away is at 2 meters depth, we are actually switched from the 0 color scale that's in the blues to the positive color scale in the yellows. And so this whole higher area, foothills and Brooks Range, is actually at 2 meters depth even, not frozen anymore by like 2100. And to make that a bit more geomorphically relevant, I'll sort of repeat. Now we're not just looking at thermal state. Now we're looking at like at what depth would the active layer sit. And the scale for this century is like between 0 and 1 meter. That's very familiar to me. Like we did quite a bit of field work in, not quite here, but like along this zone where like everything's like 30 centimeters, 40 centimeters, that kind of depths. It's a little warmer, as I was showing you when you go inland, so that's a little deeper. So the much more extreme scenario is here at 2100. The scale is now jumped to 3 meters, and you can see that there's like that thaw front has really like penetrated much, much deeper into the subsurface. And so if everything would be unconsolidated, you would have like 3 meters more of soil column in a lot of the uplands of this basin. So what you already saw from these visualizations where like the uplands like sort of like lit up more is plotted here in a bit different way. So like elevation is now on the x-axis, and then the trend in the active layer thickening over the full 200 years is what's on the y-axis. So, and you can kind of see that these sort of the foothills into the middle mountains is where the active layer thickening is the most dramatically changing. Is that due to temperature changing in that zone more fast? No, not. So what is it then? So, and that's cool, right? We can pull this out of the model. So we can like go back and see like, well, the snow depth trends are distinct in this area, and snow being an insulator, it's actually if snow is thickening, anyway, if snow is thickening, then you have more insulation. If the winter is warming a lot, then that snow might be less efficient or more efficient. So this is a complicated relationship with the snow and the soil temperatures. What is a little more obvious is the volumetric water content is low in those areas. So the way I picture this is the plains are soggy. They are waterlogged in the summer. The soils are drier in the uplands. And so drier soils are easier to warm in general. This volumetric water content is the average over the year, right? Like every soil will go through a cycle in these areas. So interestingly, so like now we have an idea of like maybe we have more volume of mobile regolith, for example, right? And that happens in like the 700 to 1700 meter zone. This is like my box over here where the active layer thickness changes most. But it turns out that the carbon content that you expose is actually higher in sort of the lower parts. So that's just how the carbon is stocked in the landscape from previous interglacials, like how the vegetation had evolved in over periods of time. So if you start sort of like multiplying the two, you get like a volume of newly exposed carbon, right? You get deepening, but you also have like what kind of stock do I have at each point? And so that's what we're doing here. We are thresholding it by bedrock depth because I don't think it's not a fair assumption to say like everything is uniformly gonna like expose soil. There's gonna be a lot of places where bedrock shows up first and the thaw front just goes into the bedrock. So this is what that looks like. And so you'll see that it's much more patchy in the sense that some areas are geologically set up or geographically set up to be like carbon rich already. Others are like maybe old moraines or they're gravels, etc. And they're not carbon rich to go with. You can see here what would be over a time axis. So we start like early 20th century and we run all the way to 21st, end of 21st. And you can see what this new stock of carbon is doing. And I wanted to like sort of repeat this little last stretch of maybe the last 25 years or so loosely, where you can see that a lot of action is, a lot of new exposure is in these like foothills regions, like fairly low on the slopes, but still in the sloped regions. And so you could like assume that there is going to be some transport of that. And there's interesting work by Eitan Shalev that shows that maybe that still gets stored straight away at the toe slope of these hill slopes in that area. So what we end up is that our models are starting to cast hypotheses for us, right? Like there's sort of an idea of like, where would we have more soil being produced or more mobile regoliths being produced? Where is like the carbon, what would the carbon contributions in the landscape be? Like maybe a little bit more here in these like foothill tributaries or out of the banks in the main tributaries. And then it will start running downstream. And so with my student Lei Zheng, we also worked on like what starts happening in this river corridor. And then the last part of the talk, I will talk like when this like all arrives at the coast. So one thing to keep in mind when you like work on the river corridor is that the heat that is transported by these rivers is actually quite significant. Very early season, the water's cold. It breaks up the ice. It consists of like chunks of ice floating in the water, and it's 0 degrees or so. And that's an interesting sediment transport question right there. Like you have a frozen bed and you have very cold water. Does it even like allow for sediment to be picked up? But that's for another talk. What we will do here is like look at what does all this water that is gonna like enter into the landscape, enter into the river corridor, due in the sense of like thawing out, like changing the thermal state of the riverbed and the river floodplain. So just to give you an idea, this is like an integrated discharge and heat temperature curve for like a bunch of like large river systems. And it goes up to like 14, 15 degrees C in the full summer. But I was talking about this like period here where sediment transport might be inhibited. So we constructed a model that combines river temperatures with river discharges. And so to walk people a little bit through that, the linkage between permafrost and rivers in the north can be conceptualized as follows. When you have like complete continuous permafrost, you have very low hydraulic conductivity, and there's not really that much groundwater flow at all anymore. Like Sarah Evans works on this, I think she's here. And this image of Michelle Walford captures that nicely, right? So only will precipitation enter into like the sort of like the thin soil column, that's the active layer, once it's like deepened over the season and feed into the river. Under the river, if there's enough heat that penetrates into the riverbed, there often is a talik, and that's an area where like the permafrost is a little bit deeper because the heat capacity of water bringing efficiently heat down in the summertime. Yeah, so like imagine this as like being a little bit of a thaw bulb. So what if you start increasing river discharges and the heat flux? What is going to happen to that temperature distribution and that active layer thickness in the floodplains? And we also asked, like, if we start like shifting the timing around of river systems, how would that be different for the floodplains? So this is a bit of a different string of models. We used a more comprehensive permafrost model that can deal with frozen and unfrozen water content quite well, that Gary Clow put together. This is a control volume permafrost model. And then Lay wrote a river water temperature model that is basically a heat balance model. I'll show you a little bit. So his model is driven by meteorological data. It captures what stage the river has, so the water level in the river. It predicts temperature and then feeds that into the control volume model, and then says something about channel bed and permafrost temperature and active layer thickness. I don't need to go into like a ton of detail here. I think a lot of these components were pulled from river or models that were relatively well tested, well vetted, and even once we had put the different components of the heat budget together, we tested it for the Kuparuk River on the North Slope and found that it's actually quite accurate, even if it seems a simple approach to predict river water. But we're conceptualizing it as a bathtub with a varying water level. There's always solar radiation that comes in. If it's cloudy, it's less. There's long wave radiation going out. And then this riverbed heat flux is one of the components that's a little bit less commonly quantified normally, but it's important for us. And then the control volume permafrost model propagates that heat that comes from the river temperature into control volumes that are stacked under there. So there's like a stratigraphy to the riverbed. So if we test that against the Kuparuk River Delta, the reason we use this system is it's better gauged, or like it's one of the best gauged rivers on the North Slope. It has about 30 years of data or so, and it has a nearby permafrost station that is about 20 kilometers away or so. So we could test the permafrost model independent of river water. We could test the river temperature measurements that were done there by the USGS from before. Yeah, so like we were like looking at basins that were like a little bit more to the east before, and now we have this smaller basin that doesn't range all the way into the Brooks Range, but smaller basin. This river had been changing, so just the river discharge had been changing as of how much volume, but also like when the river started running in the early season. So you can kind of see that somewhere in May, slowly there is a change. When it's ending was even more significant, and thus the duration that water is on the riverbed is changing. When we validate that, I think I can be like fairly short. We find that there's a good correlation between measured river water temperatures and simulated river temperatures. There's not 33 years of temperature data. There's 2 or 3 years of temperature data. There's 30 years of discharge data. So when we link these two up, you will like what you see here is this is the control, basically. The ground temperature is in black and the water temperature, sometimes warmer. So ground temperature is like if you were at the boundary and there wouldn't be any water standing on your surface. So you can see that sometimes the water's warmer than the nearby floodplain when it wouldn't be flooded. You can see that the water moves every year up and down. Sometimes the side channels do get flooded, sometimes they don't. This is only like 700 meters or so. And you can see like how the warming like propagates into the subsurface. Right, so like here are some expectations. If you have a high stage and a high discharge year, suddenly you have like more warming. If it happens in a time that the water is extra warm, suddenly you have more warming that year. But that's temperature profile in the subsurface takes a while to like relax again. Yeah. Okay. So when we started experimenting, was one of the questions we asked is, does it matter if you would have an earlier breakup of this river system, or does it matter that we have more days in the fall, so late in the season, that there's still water on the land? And so that's what this sort of idealized experiment does, whereas like we basically step back the discharge in time. And like with this color scheme, you can see that the active layer like deepens when you step back from a discharge peak in the summer to like a discharge peak like way earlier in May or June, or even like very early May, which is not the case right now. And so the idea being that if you move your whole river system more into the spring when solar radiation is abundant, you can like more efficiently warm these floodplains and deepen the active layer in the floodplains, as long as you have flooding. This is another idealized experiment. Even if we did run it over this specific geometry, we were posing like, what if we have a 50% more discharge? And that sounds pretty extreme, but it wasn't actually that extreme. I think we were already at 25% over the last 30 years. Then where would you see the most deepening? Where would you see that tallig growing the most? And you can see that it's quite significant that even in the sort of like higher parts of the floodplain, so over here where there's not that often standing water onto the landscape, you see quite a bit of like deepening in that active layer, like 20, 30 centimeters out of a total of, yeah. Does it matter what kind of stratigraphy is present? Yes. And the model is very sensitive to this. Gary Clow's model, the CVPM model, is actually like really well designed to work on different grain sizes and different lithologies, but it's still sensitive. And so these thermal conductivities matter a lot. And like one of the things that I took away from it is if you start mapping what is the sort of stratigraphy of your floodplain, you get a very complex picture of like what the active layers are doing. Another takeaway from column experiments that they did is the following. If you do have a small peat layer on top, which happens often in these floodplains, you have a tremendous insulator right there for you. And so if you have a 30 centimeter peat on top of your sandy substrate, and you have more flooding happening, there is deepening of the active layer, but it's like way less deep than when you wouldn't have these insulating layers on top of it. So pretty big contrast between the exposed channel beds without peat and the areas in the floodplain that are already covered with like a peat layer. Cool. So what we found in this sort of stretch of the source to sink system is that these active layer thicknesses are quite sensitive to like how much flooding do they experience. They're quite sensitive to when the timing of that flooding is. The earlier in the season the flooding happens, the more heat can be propagated into the in a sense of changing, the more heat you can propagate into the subsurface. And so geomorphologically, I think the implications are in riverbank erosion, and they are in contrasting these like continuous permafrost river systems with discontinuous river systems, where that process has already evolved and like everything is much more mobile in a channel belt, versus these systems that are almost completely frozen over, have like very little discharge in the winter at all, and thus are sort of in a unique niche by themselves geomorphologically. One of the things that we'll be working on more is whether we can constrain thermo niching of the riverbanks. And so that would be a combination, again, of this river temperature model, but a little bit more focused on like, can we like cut the banks with heat? Much alike coastal erosion that we've worked on previously. Cool. The last little part that I wanted to sort of highlight is we're funneling material, both carbon and suspended load. I have not touched upon quantities that much, right? Through the system, like what happens when you like hit the, what we traditionally think of like the sink, the Arctic deltas. Well, they're like their own unique thing too, in the sense that often when the river water arrives, and I should say this is work that was like in collaboration with Jaap Nienhuis at the University of Utrecht and Anastasia Piliurios at Los Alamos National Labs. It was like our pandemic project. So these rivers arrive at the coast. Often the sea ice is still there. Like they all like drain north, right? So the colder, the further you are north. So to visualize that for like one of the really large river systems, this is the Lena River starting to like filter through its deltaic distributary network. You can see this, so like uncommonly, this is the ocean. It's all white because the sea ice is still present. And you can see that it sort of carves out little melt holes, but it also like funnels water under the ice still. And this is just a period of a few days in June 2019. So that idea of a delta being so impacted by ice processes is quite stunning. And the case that I'm going to make is it's also going to like impact our like thinking of like how that works in the source to sink system, and not just for sediment, but I think also for carbon. And this is where my models, the models are like hypothesis casting, and not, we don't have like full proof for them yet. But so to highlight a similar satellite image to the previous one that I showed you, this is the Colima Delta in Russia, and sort of a similar period to end of May, right? So what you see here in the tributary channels, so the river channels coming into the delta, that there's still river ice present that causes flooding into the floodplains. The Mackenzie is the sort of poster child for this, where there's an enormous amount of flooding every single year because of ice jamming. And what that provokes or causes is this exchange between the floodplain and the river being maybe a bit more pronounced than in other lower latitude systems. So there's potentially storage in thaw lakes, there's potentially exchange biochemical, and that's been documented, especially for the Mackenzie, that's been documented too. How's that going to change? Well, we will have like thinner ice on the river. We'll have maybe less of these ice jam floods, and maybe we'll decrease that floodplain sequestration again. At least that is how we've been thinking about it. At the coast itself, sea ice is bottom fast, so it's like frozen to the bottom. The water starts like spilling over it and under it. And so this is not your traditional mouth bar that we would normally like model with loss of momentum and like the sediment nicely settling out, etc. It's like a very different environment for river sea ice interactions. And so what I'm showing you in the little cartoon is that water with its suspended load and its associated carbon potentially is either going to spill out a little bit over the top, or it's going to funnel under the ice in this like large submarine ramps that are typical described for Arctic deltas. And so again, that's like a place where sequestration works a little bit different than what we are used to for lower latitude systems. So we used the sort of model data coupling framework that Jaap had set up, that he calls his global delta change framework. It's an exploratory way of looking at deltas, right? It also has climate reanalysis data and these like basin geometries. We pulled in sea ice data, and then it has 3 model data outputs: the water balance model, the sediment WBM set that Sagi Cohen maintains. It used WaveWatch 3, and it used the global tide model. And so those 3 components for each delta along the coast, Jaap has like tried to capture boundary conditions from. And then he propagates that into like sediment transport parameterizations for river wave and tidal processes. And the prediction that the model gives you is a sediment flux for each of those components. And then you can like collapse that again in sort of the traditional ternary diagram of a delta. Like, is it river dominated, wave dominated, or tide dominated? And then the last step in this sequence is that there's a comparison with Landsat data over the last 30 years or so. I'll just show you like a few highlights. What we did is we subsetted that database for the Arctic deltas versus the global deltas. And so that meant we had about 350-ish or 380 Arctic deltas, which is super uncommon. All Arctic delta papers only always focus on like the big major players. And that's legit, right? Those are the ones that like really transfer the fluxes into the Arctic Ocean, etc. But it means we have missed for a long time these smaller systems and what's happening in them. So what you can see here is in brownish color are the Arctic systems, and in bluish color is like the global database. And there's a few points that I'll will show you. One is these large systems that people normally tabulate or measure at are like here in the top of the diagram. They are the important big players for fluxes into the ocean. They're all river dominated, even if they're only active for 7 to 9 months, or the other way, even if they're inactive for 7 to 9 months, and they get actually quite less of a magnitude of a flux than lower latitude deltas. They're still river dominated. But then there's the enormous amount of little deltas that are wave dominated in the Arctic. And so I think they are like an interesting sort of unstudied part of Arctic deltas. The other thing that I wanted to draw your attention to is that actually the Landsat data is telling us that Arctic deltas have gained or changed at their river mouths less than the global deltas. And it's about an order of magnitude less. And it kind of surprised us in a way, and it didn't surprise us in other ways. And I think it didn't surprise Anastasia because she's been looking with Joel Rowland at the sort of bank erosion rates. And they've found that bank erosion is actually slower in Arctic river systems. So you have these permafrost banks that don't move as much. Another reason that we postulate that this could be explained to is that differing mechanism. There's not as much mouthbar sedimentation that like really builds at the coast that's visible to Landsat. It goes into this like under the ice, shallow marine domain. So, to illustrate that a little bit further and a little bit more into the processes, these are little diagrams that show over time, so January to January, in example reverse or example deltas, which one of the fluxes is dominant. So like these are the big river dominated systems, but you can see like this river dominated part happens while the sea ice is still there. So it's not as constructive as a traditional delta. The counter hypothesis for this is that, yes, there have been changes to these systems, but there's been increases of sediment fluxes and there's been increases of water fluxes, but there's also been an increase in erosive wave dominated fluxes. So maybe that is the model for like the smaller deltas. We don't know, these are indications from models. There are still models that are, I don't know, like exploratory models, not detailed process models. Right? So that kind of brings me to my summary of what kind of answers and questions we still have after these modeling exercises. The thermal state in these icy landscapes really does impact the sediment transport systems in a pronounced way. It's at the production scale already controls like how much mobile soil material do we even have? Where is that gonna end up in the system? It controls that at the riverbed material. How much active layer do you have in the floodplains? Do these banks get mobile over time or not? They are not now. And it will take probably a little while before they are. I think I made a case that that parts of the system, the processes are like inherently different from lower latitude systems. And that this seasonality and timing actually needs to be built into the process models. And so one of the things that I will be trying in the next year or so is to introduce a timing term to erodibility of the bed so that you can like thaw it out in a way and have it available for sediment transport as opposed to always have the same erodibility of the bed. I did show some possible impacts on the carbon cycle, and that's a much more exploratory work still. And I think there's several projects that are starting to do field work on that. Yeah. And the last point that I wanted to make, that are we seeing these rapid warming effects in the geomorphic system? And the answer is yes for some parts of the system, but there's also latency in the system. Like in the deltaic systems, we see a lot less change has happened. And I think one of the explanation factors is the uniqueness of that depositional system, and it's less visible what happens in the submarine. visible in the sense of Landsat visible, but also just the thermal state. They're still quite a bit colder than some of the hill slope terrain in the highlands. So that's also why there's still latency in the system. And with that, I just wanted to like show you that there's like all these team members and people that have contributed to this. The current crew, Abby, Ethan, and just newly recruited is Josie Archery. Is gonna work on this probably on the North Slope of Alaska in the next 2 years or so. So that's it. Oh, the codes are available. As a good CSDMS member, I'm trying to put them on GitHub. And with that, I'll open it up for questions.
All right, thank you so much, Irina. That was an incredible talk. I was interested in it before, but now I'm exponentially more interested in the topic. Okay, so as we mentioned, try putting your questions in chat first, so that Jimmy and I can monitor them. I want to give everyone a chance. Let's see. I can start off. I guess I was just wondering, is there anything in your model? I mean, do you have any metric to in your model to like to know when there's a system change, like how much warming does there have to be before the system starts behaving like something in a lower latitude? And is there anything that informs your model about that?
That's an excellent question, and the answer is no. We don't. We haven't defined sort of like when you would have like a regime change. And I don't think even the models that I was showing today, like are probably not quite sophisticated enough to like really point to these regime changes. But one of the reasons why we use that extreme climate scenario, I mean, the RCP 8.5 is one of the like more maybe even a little bit unrealistic climate scenarios. But I wanted to like see if you really perturb things, then like how does the landscape respond? And you could see in those graphs that then only in like the last 30 years of that century, like really like the system started like warming rapidly. So yeah, I think exploring these patterns and sort of like pushing them to the extreme in the models is going to be interesting in that regard, but I have not thought about like when do we really switch the regime?
Yeah.
Right.
Okay, thank you. Okay, let's see. There's a question from Madison Douglas. Really interesting talk. You mentioned that secondary channels significantly influence the thermal state of the Kupuruk floodplain. Have you thought if these processes could lead to changes in the river planform geometry over time?
We definitely have thought about that, and one of the reasons we think about it is that I think of the banks in these continuous permafrost, and I know Madison works in like a little bit more of a discontinuous permafrost basin, so a little warmer, but in these continuous permafrost environments, the banks are actually quite ice rich, especially in some places. And then we think that it's thermal processes that control almost all of their erosion. Whereas if you would start like switching that into like a deep active layer, so deep that it doesn't constrain the erosion of the bank that much anymore, you'd like get a different geomorphic response. And so yes, I do think that that's one of these changes that will start happening over the next, I don't know, 150 years or so.
Hey, thank you.
Awesome, yeah, and it looks like Anastasia had a question too. So she said, "Hi Irina, great talk. Do you think we could try to couple your temperature model, this CVPM, with something like Delta RCM or Delft 3D for geomorphic evolution?"
I mean, yes, that's exactly what we wrote in the proposal. That is, I mean, it just got funded in September, so like we're starting out with those kind of combinations. Either GIPL, which is still, it's not perfect because there's no heat exchange between columns. It's only thermal state in the vertical, or CVPM would be sort of the tools to like predict thermal state. And yeah, to like bring that back to morphodynamics is going to be very interesting, I think.
Okay. And then a question from Kristen Sweeney. Hi, Irina. I'm curious about the effect of the changing timing of discharge. You showed a plot, the yellow-green one, where the active layer thickness was increasing slowly, non-linearly, and then started increasing linearly. What is the model feedback that leads to that behavior? That was Kristen.
Yeah, I see her question. I'm like looking at it and thinking.
Okay.
That's a good question. I'm not 100% sure, Kristen. I would like have to like peruse those movies a little bit. We have like one that's more of a movie, and peruse those a little bit better. I mean, part of it is like when you move the whole discharge curve into the window of the solar radiation being like in June in the optimum, that's where like you get like your most warm river water versus like, oh, I have my like, I don't know, September events or rainfall like still happens in October, and then there's not that much radiation to warm up the water anymore. So there's non-linearity in that sense. But I'm not 100% sure that that evolves in what you're talking about.
Awesome, yeah, and then it looks like, yeah, so Sean Chartrand had a question. So thanks very much, Irina, for an incredible talk and research program. Which environmental parameters do you feel are the least constrained, but perhaps the most important for modeling the impacts of warming temperatures to permafrost melt and active layer thickness growth?
I mean, the two that are first order hard, that the model is sensitive to, the very first one is air temperature, and that's not hard to get. Or I think we always find like, oh, the reanalysis data is fairly comparable to the station data. And yes, there's deviations still in that too, but the temperature is a big control on it, and it's still like a parameter that's easy to get. So that's good news. The bad news is the soil properties and the thermal properties of the soils. The bad news is also volumetric water content. And so both of those, I think if over time we get like better remote sensing products to like sort of constrain that, our interpretations of the model input is going to improve with improving those, and the model predictions can improve that way. But that's very much like on the permafrost side of things. I think in the morphodynamics, introducing timing into sediment transport is going to be very exciting and very different from what we normally do, or what I normally do.
Okay, Paul Mann has a question. As much of stored sediments in Arctic deltas appear to hold preferentially older permafrost carbon, do you think evolution of larger river deltas may release greater relative proportions of permafrost / aged POC to near shore for processing?
I think there's a few studies that start showing that, and one of the people who would be like super excellent to answer this question, even in more hypothetical ways, Marisha Rapash. who's like part of the team that we're starting to work on this North Slope River Basin. But yeah, there's a paper by Hilton in the Mackenzie that's showing exactly that, right? That there's permafrost and like geological carbon from the Mackenzie Basin that makes it all the way out into the submarine.
Great, yeah, and it looks like, yeah, we had one more question in the chat here. So with the warming up of the higher areas, would you expect piping / subsurface erosion to occur? And how would that influence further erosion and / export of carbon in the model?
It's not in a model. I wish it were. I actually put as an honorary member on like sort of people who've been thinking about these problems, Jean-Marie Del Vecchio, and then Ethan Pierce. They are starting to make more sophisticated combinations between like more of the geomorphic like hill slope models and the permafrost state models. And so both of them would probably say like, yes, that's a relevant process, but we don't know like exactly how to deal with it in the geomorphic models and the combination yet. Like the combination that is maybe more straightforward and that we have pioneered is just hill slope diffusion and tying that to active layer thickness, and then diffusing the hill slopes differently if you have differences in your active layer thicknesses. But that's only a very first step.
Okay. Someone, I think Paul Mann just wanted to know the name of the colleague you mentioned to contact regarding the theoretical carbon permafrost release.
Yep. Type it in the chat. Mauritius, me. Everyone. It's great to like get so many questions. I mean, this talk is a sort of new compilation of stuff together, so it's actually really nice to have like so much feedback. So
it was great hearing it all tied together. It really.
Great, yeah. Well, I guess we're a little bit over time too here, so I think this is a good time to sign out. But let's thank Irina one more time for an excellent talk and a great, lively discussion here at the end. So I just wanted to remind everyone. So we look forward to having you join for additional EPSP Connects sessions. So join us for next month's session too. So look out for tweets, look at our EPSP Connects website too, and emails from Gilbert Club and other listservs as well. So thanks for joining us and joining us a little beyond this time too, but that's always good to have a great discussion. So that's it. We'll go ahead and sign off now. Thanks for joining us.